Imagine that you're running a random experiment and your experiment has n outcomes. They're all mutually exclusive and they're all equally likely. Then you can assign a probability to an event A by counting the number of outcomes that actually correspond to the event A. And if that count is little a, then the probability of the event A would be little a divided by n, the total number of outcomes. The probability of one individual outcome is just like 1 over n in that case. Here's an example. You toss a fair coin. The sample space, as before, is still head and tail. We don't allow edge results or any of the other crazy results that we could have had. So there's only 2 real outcomes here. That means that n is equal to 2. The probability of observing a head in that case, assuming that it's a fair coin, and so the chance of getting a head or a tail, they're the same, then your probability would have to be 50%, 1 over 2. If you throw a fair 6-sided die, there's 6 different outcomes that are possible. The sample space would be, the set of potential outcomes, a number of dots on the face pointing up, 1, 2, 3, 4, 5, or 6. Now, we're going to pick an event that actually corresponds to a number of potential outcomes. For instance, A could be the event that you would be observing a multiple of 3. There are 2 outcomes that match that event, 3 or 6. And so, because there's 2 of them, the probability that the number that you would see when you roll a die is a multiple of 3 would be 2, the number of outcomes that correspond to the event, divided by 6, the number of total outcomes, 6. 1 over 3, 33%. Well, what's the probability then of seeing an even or an odd number? Well, if you look at the event, the outcome of the experiment is an even number, there's 3 outcomes that correspond to that. Outcomes 2, 4, and 6. There's 3 of them, divided by the total number of outcomes, 6. That means 50%, 1 over 2. Or the probability that the number of dots that you would see would be prime. There's 3 outcomes that correspond to that event. You roll a 2, a 3, or a 5. And that would be the same thing as the probability of not seeing a prime, which is to say of seeing a composite number. Now, it's an accident that it's the same thing. What's perhaps more interesting is that the probability of observing an actual prime number would be 1 minus the probability of observing a composite number. And that sort of makes sense, right? Because if it's not prime, it's got to be composite. In this example, because there are 3 outcomes that correspond to both events, being prime and being composite, then they both have the same value, which is 50%, 3 over 6, 1 over 2. Well, let's say you pick 1,000 people, and 545 of them have high blood pressure, and this is something that has been measured. Here the experiment, or the random experiment, is, do you have high blood pressure or not? That's what you're trying to measure. So from that group of 1,000 people that you've picked and that you've tested, you will now select one person randomly. What's the probability that this person has high blood pressure? Well, if you use the classical definition of probability, the frequentist approach, you are just looking for the relative frequency of people with high blood pressure, 54.5%. And that would be the probability that you're looking for, right? You don't know which one of the 1,000 person you've selected. You just picked one of them. It could have been one person from the high blood pressure group, or one not from the high blood pressure group. There's 545 that have high blood pressure. there's going to be 455 that do not have high blood pressure. And if you select randomly, and of course here, all of the magic is in the word randomly, then there's 54.5% chance that the person you selected has high blood pressure. This frequentist interpretation of probabilities, that you run an experiment multiple times and you're seeing how often you get the result that you're looking for, how often the outcomes are in the event that you're looking for, that is, roughly speaking, how we will approach probabilities in this course. So what's the probability of rolling a 2 when you roll a die? It's 1 over 6. Yes, I mean from first principles, because there are 6 sides to the die and there's no reason a priori why one side should come up more often than the others, assuming that we have a fair die. But in practice, what's happening is we can imagine running the experiment over and over and over again. I could ask each of you to roll a die for like 3 weeks running and to record the results of each throw. And it's this idea that in the limit, as the number of experiments increases, the relative frequency of the event is going to tend to the probability of interest. Now, it's quite conceivable that if I was to ask everybody in the class to roll the die for 3 weeks running, and then we stop and we tabulate the results and the numbers, it isn't going to be an exact split between 1s, 2s, 3s, 4s, 5s, and 6. But in the long run, if we were to keep on repeating the experiment, the relative proportions would each tend to 1 over 6. And that's what we mean when we say that the probability is 1 over 6. That's the frequentist approach to probability. There's a number of rules here that allow us to compute probabilities in general. So if you have an event, any event, the probability of the event has to reside between 0 and 1, inclusively. It's conceivable that the probability would be 0, in which case what this is saying is that the event cannot occur. And the probability could be 1, in which case what this is saying is that the event always occurs. To give you an idea, what's the probability of flipping a coin and getting either a head or a tail? That would be 1. In 100% of the cases, when we flip the coin, we would get a head or a tail. And what's the probability of getting the coin floating, hovering in the air? Well, that probability is 0. That is never going to happen, at least given the model that we're using to flip a fair coin. If you have 2 events that are mutually exclusive, such as rolling a 1 or rolling a 4, it is impossible to be simultaneously rolling a 1 and a 4. It's going to be one or the other or neither. While if your events are mutually exclusive, then the probability of one occurring or the other one occurring would be what we call the probability of the union, A union B, and that's just the sum of the probabilities of each individual events. But that only applies if the events are mutually exclusive. If they're not mutually exclusive, this is not the case. Now we know that the full sample space S is going to be the union of any event you pick, A, and its complement. Right? A union A complement, that is everything which is in the event A or not in the event A, and that covers everything. A and A complement are exclusive mutually, and so when you try to compute the probability of A union A complement, on the one hand you get that this is the probability of the full sample space S, so that probability is 1, and that's from the second axiom. On the other hand, because these events are mutually exclusive, the probability of the union would be the sum of each of the probabilities. And what that tells us is that if we try to solve for P of A complement, simply by taking the probability of A and sending it to the other side, we get that the probability of the complement of an event would be 1 minus the probability of the event. What's the probability of not rolling a 1? Well, it will be 1 minus the probability of rolling a 1. 1 minus 1 over 6, that gives you 5 over 6. So, imagine you have one 6-sided die. Throw it, roll it, record the number that is shown. We'll consider two events. The event A would be the event that the number is a multiple of 3. The event B would be the event that the roll that you get is smaller than 3. These two events are mutually exclusive. It is impossible for your roll to both be a multiple of 3 and simultaneously be smaller than 3, because the only outcomes that are multiples of 3 would be 3 and 6, and the only outcomes that are smaller than 3 would be 1 and 2. And you can look at these two sets of outcomes, these two events, and you look at their intersection, there's nothing in there. The intersection is empty. So the events are indeed mutually exclusive, and if you look at the probability of one of these two events occurring, potentially both. Well, it can't be both here, but still, when we say A or B, we mean A occurs or B occurs, or potentially A and B occur, even though that cannot happen here. The probability of A union B is probability of A plus probability of B. And let me reiterate that that's all there is to it, because the events are mutually exclusive. If they were not mutually exclusive, you would have to use different formula. What's the probability of A? What's the probability of getting rolling a multiple of 3? There's two outcomes, 3 and 6, divided by 6 total possible outcomes, 1, 2, 3, 4, 5, or 6. That means that the probability of A is 2 over 6. The probability of B now, well, there's again two outcomes, 1 and 2, divided by the total number of outcomes, which is 6. So we get 2 over 6 plus 2 over 6, which is 2 over 3, 2/3, 67%. When you roll a die, there's a 67% chance that you're going to be rolling a 1, a 2, or 3, or a 6. Right? These are the 4 outcomes that are either in A or in B out of the 6 total outcomes. Imagine another situation. You have an urn, a bottle if you want. And in the bottle there are 4 white balls, 3 red balls, and 1 black ball. When you draw one ball from the urn, there's 3 possible outcomes. Either the ball is white, or the ball is red, or the ball is black. What we're seeing here is that the probability of drawing one ball which is white should be equal to the number of balls that can be drawn that are white divided by the total number of balls, 4 divided by 8. The probability of drawing a red ball would then be 3 divided by 8. There are 3 balls that are red in your urn. There's 8 balls in total, 3 divided by 8. Finally, the probability that the ball is black is 1 over 8. There's only one outcome of the random experiment of drawing one ball, which gives us a black ball. Now, what's the probability that the ball would be white or the ball would be red? Now, notice these events are mutually exclusive. It is impossible for the one ball that you have drawn to be white and red and black. It's either white or red or black. There cannot be overlaps between these events. So the events are mutually exclusive, which means that the probability of having a white ball or a red ball would simply be the probability of having a white ball plus the probability of having a red ball. And according to what we have here, that's 1/2 plus 3/8, and that gives us 7/8. You're almost certain, although not 100% certain, almost certain to draw a bomb which would be white or red. But as it happens, the rule for computing probabilities when you have a union of events is very close to the rule that you get if the events are mutually exclusive. The only difference is that there's a special component here. Where does that component come from? If you go back to the Venn diagrams, here's your A and here's your B. When you're computing the probability of the union, according to the formula, you're first computing the probability that the outcome should be in A. So you're looking at all the things that fall in A. Then you will look at the probability that things would fall in B. But there's a little region here where you've counted the probability twice. The region where you've counted the probability twice, that's the intersection. So you're going to remove it once, just so you don't count it twice. See how that works in practice. Imagine that you have some gadget that has two components in it, a component A and a component B. While perhaps from experience you know that the probability that the first gadget A fails is 20%. The probability that the second component B fails is 30%. And the probability that both A and B fail simultaneously would be 15%. Now, what's the probability that at least one of the components fails, and what's the probability that neither of them fails? So we'll write A whenever we say A fails, and the same for B. The probability that at least one of them fails, that's the probability that of either A or B failing, and that's the probability of the union of these events. According to the formula, that would be the probability that A fails plus the probability that B fails minus the probability that A and B fail. Because when we just say that A has failed here, there's a chance that B has failed and that B hasn't failed. We don't know, right? So we compute the probability of A failing independently of what happened to B. And when we compute the probability of B failing, here it's the same story. We don't know what happened to A. It's conceivable that in here we've counted instances where B would have failed, and we have that here again. So we're double counting. We remove the double counting by removing the probability of the intersections. And here it's just a matter of literally plugging in the numbers. 0.2, 0.3, 0.15, and we get 0.35. So there's a 35% chance that at least one of the components will fail. And if you don't use this term here, if you don't remove the double counting, if you're treating the events as mutually exclusive, you would add them up, 0.2 plus 0.3, you'd say 50%. That's not possible. At least not with the numbers that have been given here. If you want to think of it this way, you can imagine that you have your full sample space here as, think of it as a rectangle or a square of unit area. Imagine that this has area here S, area here 1, sorry. Then you're going to come up with an event A, which basically covers 20% of your area, so 0.2. You can think of this here as A. And then you have a component B whose area is 30%. But if you don't specify anything about the intersection, the area could be anywhere. This could be the 30% here. right? When you specify the intersection, you're saying that there's a fair amount of overlap, right? 15% of the overall area is both in A and in B. So this cannot be the right chart to describe the situation. Instead, you would expect to see something like this. Again, you imagine that your sample space is area 1. Perhaps you still put event A here as 2, so you're saying that the area of A should be 20%, 0.2, and that the area of B, I'll use the same color here, would be here potentially. As 30%, and the area that is in both, that one corresponds to 15%. So this number here would only be 0.05. That's the difference between the full 20% and what's in both, and the number here would be 0.1. That's the difference between the full area of the intersection. Right? Now I write area. In fact, this is a probability for us, but if you ever take more advanced courses in statistics and probability, you will see that in fact we do think of probability as something equivalent to area. What's the probability that neither of them will fail? Well, neither of them failing, that's the complement of at least one of them failing. So that should be 1 minus the probability of the complement of neither failing, so 1 minus the probability of at least one of them failing. 1 minus 0.35, number you have here, gives you 0.65. If you're not sure yet how this works, let me give you another example which could be illustrating the idea of the intersection of events. Imagine you go and you do the groceries. Now, if I tell you that 80% of people purchase bread when they go to the grocery, I mean, that's great. That's something that you know. It's not that surprising, right? Bread is one of the staples. And for the sake of the argument, let's say that 80% of people also purchase milk. We'll treat milk as a staple. Well, you wouldn't be surprised to find out that a lot of people who purchase bread also purchase milk, because you already have 80% of people purchasing milk and 80% of people purchasing bread. In the worst case scenario, you might have at least 64% of people purchasing either milk or bread. If milk and bread were independent purchases, if the probability of purchasing milk was not correlated with the probability of purchasing bread, then you would expect there to be at least 64% of your people who purchase both. 80% of the people who purchase milk also purchase bread, and the people who purchase milk made up 80% of the population, so 0.8 times 0.8 is 0.64. So it's not very surprising that this would be happening. On the other hand, if you look at the people who purchase wieners, sausages, and purchase ketchup, mustard, and condiments, it's not quite as frequent a purchase. Let's say that 10% of the people purchase wieners, and 6% of the people purchase condiments. Now, you'd be less surprised to find out that the 6% of people who purchase condiments, they're also purchasing wieners. Right? You don't randomly purchase condiments. You purchase condiments to eat with something such as wieners. And here the probability of the intersection of A and B being purchased at the same time, that would be pretty high, right? Now, as a raw number, that number would be small because it can't be greater than 10%. That's the probability of purchasing wieners in the first place. But there isn't going to be that much of a jump between the probability of purchasing both, purchasing either. Whereas with the milk and bread, there might be a higher jump. It's not clear whether these purchases are strongly correlated or not. The rule that we have for the sum of probabilities, or for the probability of a union, that's compatible with the rule that we had for mutually exclusive events, right? If events are mutually exclusive, the probability of their intersection would be the probability of the empty set, and that probability is 0 by the axioms of probability. So the probability of the union, that would be the sum of probabilities minus the double counting, is just, there's no double counting in that case. You're imagining a situation where here's everything in A, here's everything in B, and you count all the A's and you count all the B's, you don't have to remove the ones that were counted twice. Well, that rule can expand to more than 2 events. What's the probability of the union of 3 events? That would be the sum of the individual probabilities, but then there would be double counting. You would have double counted what was in A and in B. You would have double counted what was in A and in C, and double counted what was in B and in C. So you remove those. But by doing so, you've removed too much, because everything that was in A, in B, and in C has been removed once too many times. So then you would re-add it in here. Set theoretically, imagine that this is A, imagine that this is B, imagine that this is C. So you add up all the A's, all the B's, all the C's. By doing so, you've double counted this area, but you've also double counted this area, double counted this area, so you'll remove them. But by doing so, you've removed, or triple counted if you want, the intersection here. You need to find a way to bring it back. The one that's here. That's what the formula is saying. If you're not sure, or if you don't think you can remember that, it is not complicated for you to think of the probability this way. It's the union of A and B together with the union of C, and then you use the regular formula. The probability of the first term, A union B, plus the probability of the second term, C, minus the probability of the intersection of A union B together with C. And then you can reapply the rule to this one. And here you can rewrite this as A intersection C union B intersection C, and then you reapply the rule to each of those. Okay, after all this work, exactly this expression here. This is one of the formulas that it would be preferable for you to remember by heart. You can imagine, or at least try to figure out what the formula would be for this one. Can you extend the pattern you saw?